Hello and welcome. This video is part of a series exploring statistical techniques and methods in kinesiology. Specifically, we will be exploring bivariate correlation, also known simply as correlation. To begin, let's cover the basic setup for this analysis. Our data consists of two variables. One variable representing the physical work rate of participants in units of steps per minute, and another variable representing oxygen consumption, or VO2, in units of mils per kg per minute, with both variables measured concurrently during a 6-minute stepper test among a sample of older adults. The total sample size was 476, and these data are completely synthetic in nature, which means these data do not come from actual participants, but instead were created artificially. That said, these synthetic data were generated from summary estimates contained in the published article by Jones et al. Cited here. In this case, our research question asks whether stepping rate is associated or correlated with measured VO2 during a 6-minute stepper test among the sample of older adults. Within a null hypothesis significance testing framework, our null hypothesis is that stepping rate among older adults is not significantly associated or correlated with measured VO2 during a 6-minute stepper test. And our alternative hypothesis is that stepping rate among older adults is significantly associated or correlated with measured VO2 during a 6-minute stepper test. Before beginning the analysis, let's briefly review the assumptions associated with this test. 1. Both variables we analyze should be continuous in nature. 2. Each observation within the sample should be independent of every other observation. 3. There should be a linear relationship between our variables. 4. There should not be any outliers or extreme observations that might have large influence on our observed correlation. And 5. Both variables should be normally distributed, or more specifically, the data should exhibit multivariate normality. For this example, we will assume these data are continuous, observations are independent, and no significant outliers are present in the data. Let's now perform our example correlation analysis in R. To begin with our correlation analysis using R running within RStudio, we need to install two packages, MVN and MV Shapiro tests, that will be used in assumption checks following the main analysis. I already have these packages installed on this system, but you would need to run this line of code if your system did not have these packages installed. Next, we will read in the data. In this case, I have entered the data in as vectors directly into the editor. You would then select both of these vectors and then read them in. We will next explore the core and core.test functions by placing a question mark before each within the editor. When each line is run, you will see function documentation appear in the help pane at the lower right. This documentation details each function's call, arguments, and return values. Of note, these functions can compute and statistically evaluate the significance of several correlations, including the most common Pearson's R, the rank-based Spearman, and the lesser-used Kendall's tau. Next, we can run a correlation between steps min and VO2, or oxygen consumption, using the core function. However, this function only returns the correlation value. As such, we need to use the core.test function to return results from a test of significance associated with the correlation. We could then evaluate linearity among the two variables by plotting a scatter plot. To do this, I'm going to copy and paste in some pre-made code that will plot the scatter plot using base R. We could subsequently then test multivariate normality, an assumption of Pearson's correlation, using a multivariate extension of the Shapiro-Wilk test. which we will use first via the MV Shapiro test package. Alternatively, we could use the Henze-Zerkler's test or Royston's test to evaluate multivariate normality, as these are competing approaches to evaluate the same assumption. Let's now perform our example correlation analysis in JASP. To begin our correlation analysis in JASP, we first need to click on the 3 horizontal bars in the upper left-hand corner of the JASP home screen, scroll down to Open, and in my case, I was recently working with this data, so correlations.csv is contained in the Recent Files tab. You will likely have to browse your computer via the Computer tab to find this file. Once selected, the data will be read in and is now in JASP. You will then go to the regression heading on the top of the JASP screen, click it, and then under there you will have a classical and Bayesian subheading. You will click on the classical correlation option. Once that is clicked, you will then have your variables in the box immediately below correlation at left. You will select them and then move them into the variables box at right. Once done, by default, it will automatically calculate the Pearson's R correlation and the p-value associated with the significance test for that correlation. There is the option to select Spearman's rho or Kendall's tau correlation as well at left. We won't do that in this case, but you are free to do so if you need to calculate those correlations. You also have a whole host of other options, such as generating confidence intervals for correlation if you are so inclined. We will also do some assumption checks. In this case, we go down to assumption checks and we're going to check the box for multivariate normality, which will compute an extension of the Shapiro-Wilks test for multivariate normality. So we get the Shapiro-Wilks test statistic as well as a p-value associated with that test. We can then create a scatter plot to examine something like linearity between the variables, where we're plotting steps per minute against oxygen consumption in this instance, and a line of best fit for the regression is placed on top of that scatter plot. We could also choose to have the densities displayed as well, so we can look at the individual variables graphically to assess their normality if we were so inclined. Let's now interpret the output of our statistical analysis. As a reminder, the question we are asking in this specific example is whether stepping rate is associated or correlated with measured oxygen consumption during a 6-minute stepper test in older adults. At right, you can see output from both R and JASP, indicating the magnitude of the Pearson's correlation coefficient is quite large at 0.74992. The test of significance for the correlation utilizes a t-test with an observed t-value of 24.68 with 474 degrees of freedom. The associated p-value is quite small, well less than 0.00001, which is obviously less than our a priori alpha value of 0.05. As such, we would conclude that the observed correlation is significantly different from 0. The remaining assumptions associated with correlation analysis that we need to assess are linearity and multivariate normality of the data. The scatter plot clearly indicates a straight line pattern indicating a linear relationship between stepping rate and measured oxygen consumption. Moreover, the density plots generally indicate that both variables appear to be normally distributed. Further specific evaluation of the multivariate normality assumption using a multivariate extension of the Shapiro-Wilks test further confirms the data appears to demonstrate multivariate normality, as evidenced by the non-significant p-value of 0.22016, which is greater than 0.05. To provide one last bit of context for our results, we can interpret the magnitude of the observed correlation coefficient in terms of a standardized effect size. In this case, simply the correlation R itself. Using Jacob-Cohen's guidance, an R value of 0.1 is considered a small effect, an R value of 0.3 is considered a medium effect, and an R value of 0.5 is considered a large effect. Since the observed correlation of 0.74992 exceeds an R value of 0.5, we can conclude that this is indicative of a large effect. However, caution should be exercised when interpreting standardized effect sizes. Moving on to the final evaluation of our hypothesis, because we observed a significant result, we reject the null hypothesis. As such, there is sufficient evidence to suggest that stepping rate is significantly associated with oxygen consumption during a 6-minute stepper test among older adults. That concludes this video describing correlation analysis with examples in R and JASP.